Hi friends, today we'll see how to check the displacement. So first we have checked the stresses, and all the stresses are within the allowables for the hydro, sustained cases and occasional cases and expansion cases. Once stresses are okay, then you can check the restraint summary as well as the displacement summary. Okay. So first we'll see the displacements. So in which direction you need to check the displacement? Okay. So you need to check the displacements for the horizontal directions as well as the vertical directions. So for first you check the displacement in the vertical direction. So you have to check sustain case, select sustain, displacement and wave reports. So you'll get the displacement like this: displacement report dx, dy, dz, or x, or y, or z. That is displacement along x-axis, displacement along y-axis, and displacement along z-axis. And r-axis, rotation along x-axis, rotation along y-axis, and rotation along z-axis. So no need to check the rotations, you just check the displacement in y direction, that is vertical deflection. It's yesterday also I told the last class. So this deflection only we are going to check in vertical. I mean, in between the if two supports or the so how much the pipe is deflect. This only we are going to check. We'll call it as sagging. Okay. So for this, what we need to do is double click this displacement in y direction, and it will show the maximum displacement at the top. Okay, again if you double click, it will show the minimum displacement. Okay, so you have to check the displacement in minus direction, that is in negative y, minus y, because sagging means it will be in y direction only. So okay, and if it is in positive direction, then the support is lifting off, maybe that location is lifting. So you have to check the deflection in y direction. So here you see the maximum deflection is 0.988, that is within 1 mm. Okay, so generally this deflection it will be provided in your stress design basis. Okay, in the stress design basis, the maximum allowed deflection in sustained cases 12 mm, 10 mm, or depends on the client requirement. Okay, but in the power plants, for power plants as per B31.1, the maximum allowed deflection for the streamline is 2.5 mm only. Okay, so as a good engineering practice, what we are following is up to 3 mm we are maintaining in the sustained case. If it is goes beyond 3 mm, what we need to do, we need to check the feasibility of addition of supports. So in order to avoid, to limit the deflection, you need to add supports only. Okay. So in this case, maximum deflection is at node number 5100. So you can check in the 3D plot also. Here you see this is 3D plot. So if you want to check the deflection in 3D plot, is maximum deflection is here only. Go to top view. At this junction, it is minus 988. Okay, at this location. Oh yeah. Then what we need to do, we need to add some support, because 0.98 is not an issue. Okay, that is well within the limits only. Okay, but if you see, we will check while checking the nozzle loads, we'll come to know. Okay, so what is why we need to add support here. So now in CAESAR, what will happen means it will not show any deflection, something like that. But in practical thing, what will happen because of the valve, this portion I'm talking about, particularly this portion, because of the valve, this may come down. This pipe may deflect like this. Okay, we will see in the animation also. the deflected or deflected shape you can see. See, there is a little bit deflection, okay. But if any valves are there, you have to add additional support because the loads will be transferred to the particular nozzle. That we will see on during nozzle limit, nozzle check. Okay, that is well within the allowable. Now we will see the animation. We will see whether it's showing any deflection or not. But in sustained case, you have to check thoroughly. One minute. If you go to sustained case, we will see. You see the deflection. Even though the deflection is 0.99 mm, but you need to add one support here. We will check. We will see while checking the nozzle loads whether the supports are really required or not. Definitely the supports are required because any discharge line, if it is going up and again coming down, you need to add one support. Okay, and with the valves are available nearby. And here also you see the pipe is coming down. And in horizontal direction also we may need some support. Okay, like this we need to check the sustained cases. For example, yesterday we have seen at some locations we have removed the support. The last video we have seen. 1 minute. Okay. So now I am going to remove this support. We will see what happens. Whether the deflection will be more or not. We will see. Sustained case. First you have to check the stresses. If stresses are okay, stresses are okay only because it's not showing any red color, no. And then check the deflection, displacement, dy. See, minimum changes mean minus 1 mm only it's showing, but definitely we need support. CAESAR is just a tool only, so practically we need to think and do the analysis. CAESAR just it's a tool, so based on your experience and based on your site experience, so you need to add the support because you see the entire length from here to here. From here to here, it is unsupported with two walls and many flanges are there. Okay, so definitely the support has to be provided. We'll see in some other cases whether it's having any impact or not. Okay. So then once the sustained deflection is okay, it is within the allowable means we need to check the horizontal deflection. For small such a small lines, there will not be a big problem in the horizontal directions because in horizontal directions for the pipe rack lines, the lines running on the pipe rack or the main steam lines only will have the issue of thermal expansion. So now we'll see. So horizontal directions, you need to check the maximum design temperature case, because that only will have more expansion. If temperature is more, your expansion will be more. So based on your thermal coefficient, your value means the temperature of the pipe will increase, and then your expansion also will increase. So you need to check displacement, horizontal displacement in maximum design temperature case. So you have to double click this dx, so only 3 mm, and again double click, you will get the positive and maximum positive value and maximum negative value. You have to check the horizontal deflections for both dx and dz. Okay, go to dz, double click this dz, so maximum is minus 2.3, that is okay, and maximum z dz in positive direction is minus 0.948. So in the 3D plot also you can see dx, check dx. Okay, dx is how much it is, point, I mean 3.8 only. So if we enter this one, then your next value will be appeared. Okay, press enter. I am just enter like that. So you will get the next values. Okay. So if you want to check the displacement in dz, maximum dz you select, and here is the maximum dz, that is in this direction, horizontal direction. So that is okay. So generally, what is your allowed displacement for sustain? It will be provided in your design basis. But for a design case, no, or design temperature, generally the maximum horizontal deflections will not be provided. Okay. So in those cases, what we need to do, based on your experience or based on your previous project or client requirement, what we need to do, some thumb rule is there, or as a good engineering practice, what we are following means, in the axial direction, maximum is 100 mm. So maximum allowed displacement in the axial direction. Axial means along the axis of the pipe, that is 100 mm. And in the lateral direction, it is 25 mm. Okay. So axial direction means this is the axial direction. Axial direction. For example, in this case, it is in x direction. So for this line, this is the axial direction. For this line, this is the axial direction, both way. Okay. So for this case, this is axial direction, and for this pipe, this is a lateral direction. In this pipe, so this is a lateral direction, that is z direction, plus or minus z. So plus or minus x is axial direction of the pipe, and plus or minus z is lateral direction. So generally, lateral direction allowed is 25 mm and axial direction is 100 mm. This is a general practice we are following. If there is no pipe, for example, if the line is going on the pipe rack like this, or if it is a header, one header is there, big header. So both end is having maybe end cap or with blind flange, anything. Okay. So there are so many branches. Okay. Like this, so many branches are there for this header line. So what we need to check? We need to check the displacement along this direction and along this direction. Okay. So if it is a free end, if there is no branch connection, or if it is a free end, then you can leave more than 100 mm also, because it will not be clashed with other pipes. Okay, if it is a free end, you can move, I mean, you can leave like this, and you have to check the displacement at this T, near to the dead end of the pipe. Okay. Okay, so in these cases, it is okay, you can allow 100 mm or 150 mm something like that, but you should not allow more displacement. Okay, for example, if a line is running like this, 1 minute, I will show you some expansion loop like that. Yeah, for example, if something like this, so what will happen means this pipe will move in this direction. Okay, so this pipe also will move in this direction. So all pipe will move in this direction. So what happens means, so the space between the two pipes you need to check. For example, if the outer pipe will have more expansion, this pipe will have lesser expansion, means there is a chance of clash with the other pipe. Okay, so it may interfere with the other pipe because of the expansion. For this case only we are allowing up to 100 mm because there will be 100 mm space, I mean, between the two pipes, I think so. So you need to allow maximum, you need to limit up to 100 mm. That is a good engineering practice. Below that also it is good only. Okay. And also why we are checking that limiting the displacement means the shoe will be there. Now, for example, if not here at the end, I am talking about the end of the. I will show you some. For example, if you take this line, you see there are many lines. So there are okay. So 1 minute. In this, your expansion will be in this direction. Okay. So you see at the end only we will have expansion. We will have expansion at this direction. Okay. So here you need to check the shoe length. If any shoe they are provided, you need to check whether the shoe is okay or not. Because if we have more expansion, what happens means this shoe also will move along with the pipe. Okay. If it is moving along with the pipe, what happens? Sometimes it may go away from the steel. Okay. For this, we need to check the displacement at each support location near to the end of the bend. Okay. So what we need to do, if the expansion is more, we need to increase the shoe length. So the general shoe length pipe, I am talking about pipe shoe. I will explain you what is pipe shoe and all, the pipe support engineering. So the pipe shoe length will be increased based on the expansion. So general standard length is 100 mm. So they will increase by 50 mm, 300 mm, sorry, 300 mm. So 300 mm means they will increase by 350 or 400 or 450 based on the expansion. Okay. And also you should not provide any guide here. I told you, in the expansion stresses, because your expansion will be more here. If you arrest this expansion, what happened? There will be a failure at this elbow location. Okay, in the expansion case. So we need to check properly the displacement. Displacement is very important for the long run lines. Okay. So how the displacement is calculated, horizontal displacement, how to calculate the horizontal displacement. So if the displacements are okay within the limit, it is within 100 mm in the axial direction and if 25 mm in the lateral direction, then it is okay. Okay, so if it is in the lateral direction, if it is 25 mm, then it is okay. Then how to calculate the thermal expansion means, 1 minute, I will open on one CSF file. Okay. So we will see this file. This is one of the streamlines we did. Okay. So here, so how to calculate the thermal expansion? Thermal expansion calculation formula is L into alpha. So what is L? L is distance from the anchor support to the bend or anything what you want to calculate. For example, in this case, if you want to calculate the displacement, if you have any anchor support, anchor means limit stop or something like that. Okay. So 9690 9450 here I took, I think so, 9450 9450 to 9510. Okay, so here this is approximate calculation only, mean you'll get a nearby value. Okay, so from here to here we are going to calculate. So what is the overall distance of this? From here to here is 18150. Okay, so I already calculated this value. Okay, so what is L means 18150, that is the distance between anchor and where we want to check the displacement. Okay, which location we want displacement at this location, we want to calculate displacement at this location. Okay, and then alpha is linear thermal expansion mm per meter as per P31.4 table C2. Okay, this is a table C2 from ASME B31.4, and for carbon steel, because this material is A106 grade B. So for A106 grade B, you have to check the material as well as the temperature. So what is our temperature? Our temperature is 300 degree. So our temperature is 300 degrees centigrade. Okay. So for 300 degrees centigrade, so for 300 degrees centigrade and ambient temperature is 21. So this delta T is delta T. Why we are not going to multiply this one? The formula is L into alpha only. So this alpha only we will consider from this delta T value. What is delta T? Delta T is the temperature difference between design temperature and ambient temperature, or whichever temperature you want to calculate, that minus your ambient temperature. Okay, so in this case our ambient temperature is 21 degree, because if you go to special execution parameters, you can find our ambient temperature is 21 degree. So our ambient temperature is 21 degree and your material is A106 grade B. So from you will get delta T is 300 minus 21, you will get 279 degree. So for 279 degrees centigrade, you need to calculate the alpha value. Not calculate, you need to take the value from ASME B31.3. So the alpha value is 3.448. It is given. For exact value. So for 275, it is given as 3.4. Okay, here is it. For 275, it is 3.4, and for 300, it is 3.7. Okay, and for 279, the calculated value is 3.448 mm per meter, because you see the unit is in mm per meter. So what we want is, we want in mm. So we have calculated, we have converted this one mm per meter into mm per mm. That means divided by 1000, you will get 0.003448. Okay. So if you multiply this with this, then you will get the thermal expansion value. Means 18150, because both units should be same. mm means then only you will get the thermal expansion in mm into 0.003448. So we'll get 62.5 in mm. So we'll go to the particular node. This is node number is 69510, and in the output, go to output, CAESAR output, I'm just selecting from here itself, and this particular case T4, so sorry, load case 4, select displacement, wave reports. Okay, go to node number. If you want to find the node number, double click this, it will get minimized. Then you go to here, find 9510, type here 9510. So you see in the X direction, because it is in X direction only. So in X direction, how much it is? 62.198. So what value we got? 62.5. So it is approximately matching. Okay. So like this only you need to calculate the thermal expansion. If you don't have the CAESAR also, you can calculate manually like this. Okay. For equipments and all, we have calculated like this previously when we don't have the. I mean, some cases what they used to do, the client in some power plants and other plants and all, what they ask us to do means we should not model the equipment. We have to just give the displacement of the nozzle. So the nozzle calculate thermal displacement will be calculated based on like this only. I will show you while checking the nozzle allowable load for equipment. Okay. So you see, so like this only we have calculated this one. Okay. So like then once displacements are okay, what we need to do? We need to check the restraint summary. So before that, what I would like to tell is how to calculate the thermal expansion of the loop, or how to calculate this length of the loop. Okay. So there is no proper method for this calculation, expansion loop length calculation. Just we have some approximate methods. So one is guided cantilever method. So how to calculate? See, in expansion loop, there are different types of expansion loop. So why we are going for expansion loop is, first you need to see. First you need to see, for example, if you take this line. Here we'll see how to design the expansion. There is no proper calculation calculate the expansion loop. Anyway, we have some spreadsheet based on the some of the reference books. Okay, I will show you one of the calculation. This is a book from Mr. L.C. Payne. Okay, so based on this, the loop length has been calculated based on the guided cantilever method. There is a method called guided cantilever method. So what is cantilever? Cantilever, I will show you what is guided cantilever. So this is a normal cantilever. One side is fixed, the other end is free, and load is applied in the downward direction. Okay. So this is a normal cantilever beam, and this is a guided cantilever. Means up to certain extent only it can the deflection will be there in the downward direction if you apply force. So based on this method only, we are going to calculate the loop length, that is the perpendicular length of a loop. So generally, why loops are considered? What is the purpose of loops? Expansion loop. For example, if you take this line, this entire stretch is, this is, if you take this bend from this bend to this bend, so it is around 114 meter. It is around 100 meter, and if you see the temperature is around 300 degrees centigrade. Okay. So for 300 degrees centigrade, if you calculate the expansion for 100 meters, then you will get the overall expansion of the pipe for 100 meters. Okay. So generally I told, for horizontal deflection, for horizontal maximum is 100 allowed. Okay. So if it goes on beyond 100 then what we will try to add expansion loop in order to reduce the horizontal deflection. So how this loop will behave means, I will show you. First, we will see how to calculate the expansion loop here. So based on this method, okay, the formula for calculating the expansion loop is given as L equal to, this is loop length, square root of 3 ED by S into delta. Okay. So this is a formula they use to calculate the perpendicular length of the loop. Perpendicular length is nothing but this is a perpendicular length. So when for this straight line, so this may be the perpendicular length. So this is a perpendicular length. So in order to get this perpendicular length only, we are going calculating this one. So this perpendicular length only, it will absorb the expansion caused by the pipe based on the temperature. Okay. So it will absorb. If a perpendicular length is more, then it will absorb more expansion. Okay. Okay. So that depends. This perpendicular length is depends on the expansion and depends on the feasibility on your layout. So you have to check the layout also. So whatever you want, you cannot give. For example, if the perpendicular length, whatever you are calculating, if it is coming 10 meters, so you cannot extend the loop to 10 meters because we need to see if any obstruction is there or any roads or there like that. You need to check the layout and 3D model. Okay, so you cannot blindly go as per the calculation. So I will show you. So this is a perpendicular length, and S is allowable stress, and L is the length of the leg, and delta is thermal expansion, and E elastic modulus of elasticity, and D is OD of the pipe. Okay. So in this, for example, we have considered this pipe only. So the design temperature is 300 and ambient temperature is 21. What is the material? A106 grade B. So for A106 grade B, alpha well linear thermal expansion, this we have seen how to calculate the horizontal displacement. So in this, from 279 degree, see, from table C2 ASME B31.4, we will get the value of alpha, that is linear thermal expansion coefficient value. So okay, so that value I applied here, and after that what we need to do, we have to apply the formula. This is square root of 3D by S. Okay, or 66, any formula can be used, 66 into D into delta. So whatever what is the value we are getting here is, so this modulus of elasticity you can consider from 31.3, or here also it will be available. Okay, this is your modulus of elasticity for hot condition, means for the particular temperature. For 300 degree, this is your this is modulus of elasticity 18258. So what we will see here, 5248 Newton per mm square. Okay, then so all I have kept in mm only. So then only we will get the value or a length of the perpendicular leg is in mm. Okay, and allowable stress value you have to take it from 31.3 table 1, and a length between anchors. So this is approximate value I have provided. So this length between anchor is that you have to check, you have to verify. So where we are going to provide the anchor. Anchor means this limit stop. Okay. So what we will do, for example, this line. Generally in analysis, I will show you how to fix that one. Okay. First we will see this calculation. We will complete this, and I will show you how to do, how to fix, how to provide the limit stop, or okay, and how to provide the expansion loop on the pipes. We'll see. So here length between anchors, there will be two anchors before and after the loop. Definitely two anchors should be there. Okay, here one anchor and one anchor. So the distance between the two anchors that we have to enter. So based on this anchor only, the expansion will be there. Okay, I will tell you. Okay, so if we enter all the values, then what we will get means we will get the perpendicular leg length, that is around 12 meters. As per this, the perpendicular length is required as 12 meters. So 12 meters we cannot go. I think loop will not be, we will not model a 12 meter, no, because if any loop obstruction will be there, so there are a lot of things. So you need to check the accessibility or feasibility at the layout. For example, if any loops are required here, means if it is free, it is okay. Then 12 meter it will obstruct overall length. Okay, so you cannot go by 12 meters. So this perpendicular length is, for example, in this case, what we have done, what is the length of the loop? 2.5 and 2.5. So 5 meter. So here 5 meter and here 5 meter. So totally 10 meter we have accommodated here. Okay. So this loop length 10 meter. Don't go exact value. So we are given here is 10 meter. So at least below that, near to the value, you can maintain 10 meter or 11 meter, or by adding these two legs. This is one perpendicular leg and this is one perpendicular leg. Okay. Okay, so two perpendicular lines, just 5 meters we are consider, or 4 meters also you can consider, or 3 meters if you consider, then you have to add one more expansion loop. Okay, so this is as per this reference book. And one more, we have a lot of spreadsheets. So based on your project requirement, you will have a lot of spreadsheet. Okay, so you have to discuss with the client and get the loop length calculation sheet if available. Generally, loop length calculation spreadsheet will not be provided by the client. So what we will do, we will calculate as per the CAESAR requirement, as per our requirement. Okay, so I will show you. First I will remove the expansion loop, then we'll see. Okay, how to start this one. Okay, so just I'm so this is a very big line. This is a steam line for a steel plant. Okay, you see how many loops we have provided. You see the temperature, it is 300, but from here onwards it is 495. If you check the material, then it will not be carbon steel material. It will be A335P11 alloy steel material. Okay, so our material selection is very important. Okay. So now I'm going to delete the loops. We'll start from scratch. Okay. (9980). Okay, so from here onwards it is coming 9750. Delete this bin. So enter this node number as 9750. Okay, then here one bend is there. Delete this 9830. So here you have to change it to 9830 because that continuation should be there. No, otherwise this will be free. This node number and this node number is nowhere connected. Okay, so if you make like that, so if you don't change this one, if you maintain 9870, then that will be wrong. Okay, then I will remove this loop. Okay, I will remove this loop also. Okay, then we'll see. After that we will add one loop here. Okay, just I'm selecting and deleting the loop, sorry, the perpendicular leg. Nine five one zero. Okay, 9510. Then your bend is remove this bend and you change next from number to 9590. Since we have deleted in between, no, so you have to be careful. Okay, so now so the limit stops are there. You see, generally before and after, for example, any loop is there. So before and after an anchor is must. Okay. So I will show you what happens. Here there are three limit stops. Two loops are there, no? So before and after. Here one limit stop is there, that is an anchor. One more is here, and one more is here. Okay. So now I'm going to run this system. Generally, without limit stop only, you have to run initially. I will show you what happens if you provide more than one limit stop at the same leg. Since this is a somewhat big system, so it is taking time. Okay. Okay, there is a failure. You see, in an expansion case, there is a failure. Okay, we will see where the failure is happening. Go to 3D plot. And select the expansion case where the failure happens and select overstress point. So you need to see here, it's showing full red color because of the number of limit stops. So in one direction there should be one limit stop. Okay, don't go more than one limit stop. For example, if a lengthy line is there, means maybe at the center you have to provide one limit stop. Okay, so don't go like this, three limit stop to avoid the expansion. So now if you check the Z direction, X direction, no? Check the displacement. There is no, see, the displacement has been reduced because of the number of limit stops. It is well within the 100 mm, but that is not a correct way. Okay, so you should be very careful while doing this. So some people used to say use limit stop to reduce the expansion. That is not a correct method. Okay, if you check the displacement here, see the displacement is 95 mm. So it is within the allowable only, within 100 mm, the axial direction. Okay, don't go like this. We should use only one limit stop in one direction. Sometimes it will not show failure also. If you use one or more limit stop at one direction. So then you cannot tell then CAESAR is not showing any failure. So shall we use a limit stop, two limit stop at one direction? Means that is not a correct way. Okay, so don't go like that. So now I am going to remove the limit stop. Then we will see what really happens this line. Okay. So now I am telling the basic things only. So everything. So the method also it will vary from client to client. Okay, some client requirement may be different. Maybe you take some big clients and all. Some client requirement will be different. So you have to follow as per your specification. Okay, I'm telling the basic concept. If you understand this, then your For other methods also, it will be very easy. Okay, so just run the system. Okay, you see now the stress failure is not there. We'll see the stresses. What is the percentage? And maximum, you see, it is around 72%. That is well within the allowable only. Okay. So if you double click this, you will get maximum. It is 72.7 only. We'll check the displacement. That is a maximum design temperature only. In this project, we have used only one temperature since this is a power project. So we should have used 31.1, but I have changed the code to 31.3. I will show you in 31.1 also what will be the result. So you have to check the displacement in horizontal direction. Dx, double click this dx. Again double click. You see the displacement is 297 mm. Okay. We will see where the displacement is coming. Okay. So we'll see. Here in the 3D plot, so you have to do the pipe rack line like this only. So it will be a plain straight line only. Initially, I will show you. So for this case, for the fourth case, you have to check the displacement. So maximum displacement you see here is 297 mm. That's along x-axis. That means your pipe is moving in this direction. And if you then press enter, okay, you see it has been reduced. So your pipe is moving in this direction. That is okay. Is 297 mm. So any other limit stop is there? No. Okay. So we will see the deflection curve or deflection. How this pipe is behaving. Oh, you see, the pipe is moving like this, 297 mm. Oh, okay. And here also 146 mm is coming, you see. Okay, so our pipe is moving in this direction. That means you need to add loops. So 297 mm we cannot leave like this, no? So it may clash with the other lines, maybe, or it may clash with nearby structures or any other thing. Okay, it may abstract the way. Okay, and in DZ is 146. This is so here also we need to check. Some clients, no, they will ask us to consider 6-inch also, means 150 mm. 150 mm also they can allow, but our general practice is 100 mm. So you have to check with your client before adding any expansion loop. What is the maximum allowed displacement in axial direction of the pipe? Okay. So before proceeding, before adding any loop in the line, you have to discuss with the client, get the approval. After that, proceed with the analysis. Okay. So now we'll see. So we come to know that we have 297 mm at this direction. Then we need to see where is the null point, where is the minimum displacement. for this line, for this leg. So just enter, and we'll see at the center means what happened means this pipe, no, this is 126 mm. So all are in positive direction. These are all in negative direction. What is here? Here it is in positive direction, you see. After some location, yes. So you have to find out the null point. Null point means wherever direction change, pipe direction will change. What pipe automatically how will expand means. So up to certain limit, for example, if it is like this, up to certain limit, pipe will go like this direction, okay, and up to certain limit, and after that it will move in this direction. So wherever the minimum displacement in the horizontal direction, that we will call it as null point, means small deflection, that is maybe sometimes 0 mm, 0.1 mm like that. Okay, so here if you see here is 10 mm. It is in minus direction, okay. 18 mm. It's node number 9890 is 11 mm. 1 mm here is at node 9810. After that, at node number 9830, it is minus 1 mm. After that, you see there is a why the node numbers are getting. Oh, yeah, up to here 9590. We'll see. We'll go to the output. There we'll check displacement. In X direction we can check after 9500. So 9000 is it where maximum is at this node number 9300. Okay. So after that you can see gradual reduction in the displacement. So up to this point is at 9830 it is very minimum. After that again it is going in opposite direction and positive X direction. So this is your null point. 9830 is your null point. So always you try to provide limit stop at the initial stage. I am telling, if you provide limit stop at the null point, then you will get minimum loads on the limit stop. So if you provide limit stop at the maximum deflection, your limit stop loads will be more. Okay. So you try to place the limit stop at the center, I mean where the null point is, okay, at the initial stage. But if you provide limit stop at the null point, then there will not be any change on the end displacement. Okay. 9830. We have to check 9830. Yeah. So this is the point where the direction change happens. So from this point up to this point, what happens? This pipe is moving in this direction. After this point, it is moving in this direction. Okay. So this is the point. Okay. So you see approximately not at the center but towards this loop. So we'll see, we'll check, we'll consider this point as null point 19810. We'll provide limit stop here. So if you check, you have to check like this only. Initially, you have to provide, find out the null point and provide the limit stop. then we will see the end displacement. End displacement will remain same only. After that, what we need to do at the center, we need to add one loop. Then we will check the end displacement, if it is okay or not. If it is not okay, then we have to add one more loop. If the displacement still within more than 100 mm or around 50 mm, then we have to go for another loop. Okay. So it is so like this. If it is running continuously, so this may some engineers might have got this one. Okay. So this is non-convergence error. Generally, if you are getting like this non-convergence error, it's a non-converged loss titration, non-linear restraint. Okay, so wherever we have friction provided, no. So in those cases, it sometimes it may happen like this. This is because of the support may lift off. Okay, okay, because of the sliding of the friction. So this, I mean, it is continuously running because inside CAESAR, no, the program is in matrix format only. So once you get converged, then only you will get the result. If it is not converged, then you will not get the result. So here there are some maybe non-converged loss iteration is 5. So there are 5 node numbers. Let's say 1, 2, 3, 4, 5. 5 node numbers which is not converged. So in this, what we need to check, you have to note down these node numbers. Okay. So you have to note down the node numbers where it is showing not sliding and negative sliding. It is no 9410. Other node numbers you leave. Okay, here whenever it is showing like this 9410, do you understand? No, see, like this. If it is slowing like this, okay, not sliding and negative sliding, that node number only you have to select. You see, you just note it down 9410 and you have to check the direction. Is it X, Y, Z? This is X. Okay, this is X and this is Y. This is Z. Okay, so wherever it is showing 1, that direction you have to remember Y. You have to mention as Y. Okay. So sometimes in X or Z also it will show. If you provide friction on the coefficient of friction on guides and limits of, then it may show like that. Okay. So now it is showing in Y direction. So you have to note down that node number 9410. Okay. So cancel this about the run S. So why this configuration warning is coming means I think we have discussed. This is because of the old version. So this model and analysis has been done in the old version. Now if you open this, then it will show the configuration warning. So if you want to fix it, just fix it. Or if you want to ignore means again this warning will come. Okay. So go to fix. So it will go to the configuration settings, then editor, then you save this. If it is okay means you just save. Then go to piping input. This I could not open temp meters. So just I'm closing this. And again I'm closing. Now go to piping input and find out the node number 9410. Control F 9410. So here I think so because of this support is lifting. This support it is lifting. We will see. Okay. So what we need to do if you're getting this non-convergence error means there are two types. One, you have to remove the coefficient of friction at the initial run. So once we complete the analysis, finally you have to enter this coefficient of friction and run the system. It will run. Okay. Or keep this coefficient of friction as it is. You instead of plus y, go for y. Then you run the system. It will run. So don't give this y near to the nozzle. It will create lot of y direction loads. Vertical loads will be more. Now you see again it is running. So wait for some time. Yeah, now it is. You see, it is getting cleared. The total cases is 11. So it is current case is 8. So it is running like that. 22 seconds. Is it 23 seconds? So that error is getting clear. Okay. Okay, now what we have done, we have provided limit stop at the null point. Okay, so now if you check the displacement, it will be same only. Yeah, you see, it is same only 287. I told you no, so there will not be any impact on providing limit stop at the null point. Okay. So if you want to reduce the limit stop, horizontal displacement, so some people what they will do, they will provide because they will provide the limit stop somewhere here. Okay, somewhere here. Because your deflection is more, horizontal displacement is more, you know. So some people they will do, okay, we will provide limit stop at this location. Then you will not get the displacement at this point. Like this, if I am providing limit stop here, maybe here you can consider limit stop. Okay. And you run the system. Just I am showing what happens. Generally, people will think like that only. Some clients also they used to tell like that. If you don't know the concept, then they used to tell add limit stops to reduce the displacement. And that non-convergence errors, no, that error is because of the sliding as well as because of the lifting of supports. Okay, I have provided limit stop at some location. You see, the stresses are exceeding in expansion case. It is around 258%. It's very high. Okay. So it is not recommended to provide limit stop at the maximum displacement position. Okay, 1 minute. Okay, now we will remove the limit stop at this location. So what we need to add a loop at the center. Okay, where we have found that null point. No, maybe 9810. Maybe here. Yeah. Okay. So we'll remove limit stop at this location. We will try to add one loop here. Maybe not. This is not at the center. Maybe we'll try to add a limit stop where. We'll try to add a loop here. Okay. So 9750. If you want to insert So what we need to do 9750. That's why we are asking you to consider 20 series of node incrementers 20 or 30 like that. Now it will be easy. No, if you want to insert something, means don't give node numbers away from this one. Means 99730 to 9810 means it should be within this node numbers only. So you don't go to 10,000, 15,000, 20,000. That is not a correct way. You can give, but that looks odd. Okay, so don't go like that. So now what we are going to do, we will add a loop here 9750. Just give one bend and go to the next element. I just give 9760. So in minus x direction, we are going to add will 5 meters. We'll make it as 5 meters. Okay, and use bend, and then you enter this one as 9760. And you can change this because only one node number is there. You can change this one to 9770. 9770. Here also 9770. And here you have to enter the bend because your loop, we are going to provide one loop here. Sorry, one perpendicular length here. Okay, after that, this should move towards here. Okay, so I am going to double click this. Since there are 9780, then here what we have to do, we need to insert an element. Insert 9800. You make it as 9800 or 9790 because anyway we are going to add one support in this location. It should be in Z direction 5 meters. The same length what we have considered for the other leg we will consider here. Okay, 9800. Select bend, and here if you want to continue, then you have to give a continuation node number 9800. Okay, so you see now we added one loop, and this is unsupported. If you check the length, means it is unsupported. It is already 4 meter, so 5 meter, 9 meters, 11 meters it is unsupported. So you have to add one support here. Okay, and okay, anyway, just I am going to run this, or we will I will run this system. So like this, step by step only you have to go, and only you will get the correct results. Okay. So Jones just don't follow this. You can follow, but if you go by step, first you have to add 2 meters loop and 3 meters loop like that. This one I have directly given 5 meters. Okay, so now we'll see the stresses. See, the stresses has been cleared. And it is 72.7, that is good. And if you check the displacement, T1, double click DX, see the displacement has been reduced, but still it is very high, that is 197 mm, nearly 198 mm. So So if you keep 150 also, it is more only 50 mm more. Okay. So now again, what we need to do, we need to find the null point, because I told you, before and after the loop, limit stops should be there. Okay. So now we'll check the deflection, a vertical deflection. You have to check the vertical deflection also. So whatever I'm saying, you have to follow the same steps for every run, each and every run. You need to check the stresses for all cases: hydro, sustain, expansion, occasional, and then displacement in plus vertical direction as well as in the horizontal direction. After that, you need to check the restraint summary, and then nozzle loads. So like that, this procedure has to be repeated. If you change anything or if you run the system, you have to check thoroughly all these things, and flange leakage check, trunnion check, everything. Okay. So if you check the displacement and sustain case for the vertical deflection, for the sagging, double click this. You see the deflection is 7 mm. So for steam lines, generally as per 31.1, it is 2.5 mm only. So where we will check 9750 means this location. Okay, now it is showing 7.9 mm. We will see. So always for the pipe rack line, I will show you the, yes, okay. So it is 7.4. So always what you have to do, you just break this 9755 at the center. If you know the node number of the support, you just enter. So that is not a node number, maybe 9790. Just, what is the support node number? 9770, sorry. So break, you just enter the node number whatever in your 9770. Okay. Now what I'm just going to delete this. We'll see what is the deflection here. Okay. Or we'll keep this, and we didn't add any support here, but what is the deflection here? 9000 into 5.5 mm. Okay. Now I'm going to break this. Just break and we'll see what is the deflection. Okay, I will tell you why we are doing like this. Okay, now we'll see the deflection. In sustain case, double click this 9798 and where is the screenshot here? So previously at 9749, you have maximum deflection 7.4. Now 9748 has been reduced to minus 3.5 after introduction of one support there. Okay. Now at 9798 it is 5 mm. Previously at 9798 it is 5.8 mm. We need to add one more support there to reduce the deflection in vertical direction within 3 mm or 2.5 mm for the steam lines. So we will add one more support here. So generally you need to break. What client used to tell me, for any system, if it is running on the pipe rack, so you need to check the midpoint, deflection at the midpoint. In the design basis they used to mention, you need to check the deflection at the midpoint. at any midpoint. Okay, at least 2 to 3 supports you need to check like this. Understood? No, I mean, because if you check the deflection at this midpoint, there will be a small difference between the straight portion, or if you I mean divide this portion into 2 or 3. Okay. So now we added support. Still the deflection is the horizontal displacement is more. Okay. Generally for the streamlines, every 30 meters we used to provide expansion loop. That is a general concept. That is a thumb rule. Okay. So here total is 100 meters. At least 2 loops are required. Okay. So now what we need to do, we need to find the null point for this support. So for this line, where is so here also what will happen for this leg, the same, you will see the deflection. What is the node number? Horizontal displacement 93902 9750. Okay, so there is no limit stop, you see. Yeah, yeah, we have removed the limit stop. 93902 9750. Find 9390. So 9390 is minus 194 mm. It is coming 9300. Where is 9300? It's and all 9300. Okay. After that, you see in at 9670 and 9690, there is a direction change. You see 9670. Sorry, 9670. Yeah, from this onwards, you can see a direction change at 9690. Okay, so either you can give limit stop here or here. Okay, so already they provided limit stop here, and after this, again in this direction, you need to check the null point from 9890. 9890. Yeah, at 9950 there is a direction change. That is a minimum displacement. 9830 or 9850. So any one location you can give. I'm going to give 9950 limit stop. Okay. So like this you need to check. Again you need to run the system. Okay, now we'll check the expansion stress. It remains same only, because we have added limit stop at the null point location only. So the stresses and displacement will be same. You see, oh, the 215 has been increased at this location, 9388. Sorry, 9388 means it will not be 9388. It should be 9390. Okay. Okay. So what we will do, I mean, after adding one loop, then also our displacement, horizontal displacement is more, means you need to add one more loop. Okay, then only you can reduce the displacement, horizontal displacement. For that, we have found the null point in this case. Okay, so here we found the null point. remove this. So we need to add some loop here, somewhere here or here. So if you provide here, it is very close to this loop. So what we will do, we will add some loop somewhere here, so that you will get minimum deflection displacement at this location. Okay, so we will add here on loop. It will be okay, no? Yeah. So now double click this. Sorry, I mean use bend, then insert. We have to add an 9520 perpendicular leg minus 5 meters. Just okay. Double click this. Then here you need to change the node number to 9520. So you keep this same. Here you need to add the bend, and again you have to use the node number. Go to next node. Okay, so now what we have to do, just insert an element 9610 or 9600, anything you can give. 5 meters, the same deflection, and 9610, the previous node number you have to enter. So now we will add support here, because already you see, no, the deflection is more, vertical deflection is more on the sustained case. 95152500. So 9770, I think previous sorry, and control P, 2500, 9770. Okay, so always you have to provide guide support here before and after the loop, means start and end of the loop. So you have to add guide support. Now, because your loop, how it will behave means like this only it will be behave. So in order to guide properly here this direction, we are adding guide support here. Like this. So now your maximum deflection, displacement will be here only. Okay, here and also here. So all bends you need to check. Okay. So now we have added one loop here. So again for this loop, one anchor support should be here, and here also one anchor support. Already we have found anchor support here. No. So we need to find the null point, or I am just giving at the center 9690 limit stop. Okay, and here I am going to retain the same location. Already this has been provided. Okay, now we can check the displacement. So like this, you have to check the displacement for pipe racks or pipes running on the sleepers, for long run pipes and all. We have to add loop like this only. First, we need to check the overall horizontal displacement at the end point. Okay. So based on that, you have to find a null point, add a limit stop over there at the center. Okay. Then you have to check the displacement, it will be same only. So at the center you introduce one loop and you check the deflection, horizontal displacement at the both ends. So if it is okay, then you leave it. Otherwise you need to adjust the loop, this loop towards right side, and you need to introduce one loop on the left side. Okay, so now we will see the deflection. First we check the stresses. It is same only 72.7, and displacement. Main thing is important. Important thing is displacement here, because So you see, it is well within the 100. So that loop is working. This in Z direction, it is somewhere not in our node number. So it is somewhere. So maybe they kept like that. The client might have accepted for that one. Okay, you see, that node number is 8580. I think already we have seen, no? So somewhere here, the deflection is more. Yeah, this one, 8580. So you can leave like this. Okay, so here, I think you might have understood the concept, no? So first, for straight line, you have to find the null point and introduce a limit stop, and you introduce a loop here. Okay, so once you add the loop, you have to find the null points before and after, and add limit stops. Okay, so after that, what we need to do? If this loop is okay, if one loop is okay, at the end the displacement is within 100 mm, then you can leave like this. If the displacement is still more than 100 mm, then we have to add one more loop like this. Okay, and you have to check, you have to introduce a limit stop before and after, here and here. Okay, so for two loops, three limit stops. It is for one loop, one limit stop and one limit stop, and for this loop, one limit stop here and one more limit stop is here. Okay, so you have to always remember to provide the limit stop at the correct location, because if you provide limit stop, for example, if you check the limit stop, what is 9450, if you check the load on the limit stop, I will tell you how to check the loads. Okay, so now we have seen, so what we have seen, so for we have checked the stresses and displacement. Okay, displacement in vertical direction as well as horizontal direction. For horizontal direction only, this loop requirement, if loop requirement is there, then you have to add the loop. Okay, and third one is restraint summary. How to check the restraint summary, that is pipe support loads. So for restraint summary, what we have to do, we have to select okay, for restraint summary, what we need to do means, we need to check, we need to consider hydro, all operating cases. Then I will go back to the old one, that our model, our pump model. Okay, so now, 1 minute. Okay, before that, I will try to complete this one portion. So here, I told you, no, midpoint, how to check the midpoint for all the pipe rack lines running on the pipe rack. You have to just break this one into two, and you have to check the deflection at this point. You just remember 9440, and somewhere, anywhere you can check. Just randomly you select any place. Okay, so you have to remember that node 9700. Anywhere you can select. Okay, just 9050. So what are all the node numbers? 9050, 9700, correct, no? Nine four four zero. Okay. 9700. Okay. So we just run this one. And I will tell you how to model the lines on the pipe rack. It is very simple. Okay. So don't go one by one. If you know overall length of the entire line in one stretch, so we can model and you can break into number of elements. So like that, if every 6 meter support is there, means you can break into every 6 meter, and then you add support accordingly. And if you want to change in between, then you can check 1 to 1. Okay. Now we check the displacement in sustained case for the selected node numbers where we have broken the nodes into two. That is the midpoint, where we are going to check the deflection at the midpoint. So what is the node number? 9050. First is go to 9050, 9050. It is 0 only. You can leave. Then 9440, 9440. It is very less, 0.339. So it is well within the allowable. And 9700, 0.319. So it is okay. Okay. Just to verify whether the limit, I mean, the deflection is under the limit or not. Okay. So this is a general practice in all the projects. Okay. It will be given in your design basis. Some client used to comment on this. Okay, if you are not checked properly. So then at what we have seen, this point, that non-convergence 9410. Previously what we did, we used, now we will see remote the Y. Okay, we will see whether it is running or not. Oh, now it is running, you see here. Okay, if there is no sliding error, then it will not show like that. So you need to see there are two options. One is to remove the coefficient of friction and run the system, and once you complete the analysis, at the final stage you need to add the friction at that particular node. And again, if you run, it will run. So you will not get any error for that. Okay, so now we will see. We'll go to the pump model. We'll see how to check. Pump suction discharge. Okay, so here go to the output. Now I told you how to check the restraint summary. The third one is restraint summary. The fourth one is nozzle loads. I will tell you. Okay. This restraint summary will show what is restraint, that is supports only. So for restraint summary, you need to select hydro operating all OPE cases. OPE. Okay. Don't select all sustain for this. Then consider all OPE cases and then sustain. So these are the cases you have to select. Okay. In some projects, the client used to mention what are all the load cases to be considered for support loads, and what are all the load cases to be considered for nozzle loads. Okay. So it will be provided in your design basis itself. Then select restraint summary extended. All are same restraints extended, local restraints, and restraint summary and restraint summary extended. So there will be a difference between restraint summary and restraint extended. Restraint summary only it will show the forces and moments, Fx, Fy, Fz and Mx, My, Mz. Okay, you see, Fx, Fy, Fz and Mx, My, Mz. And in restraint summary extended, it will show the forces and moments and displacement. Okay. Fx, Fy, Fz, Mx, My, Mz, dx, dy, dz. Okay. So now we will see what is Fx, Fy, Fz and Mx, My, Mz, M. Okay. So first we have to see whether the support, all supports are taking load. That means I will show you. If this is the case, you need to check the loads in vertical as well as horizontal. Okay. For example, at node number 210, we have provided rest support. We have given rest support. So only we have provided rest support, but in Fx you are getting some loads and in Fz you are getting some loads. This is because of the friction, coefficient of friction only we have provided. Okay. So in the vertical, if all loads are in negative direction, means the loads are in Newton. Okay, if it is in negative direction, then the support is resting on the steel. Okay, then if you check the displacement, why we are checking restraint summary extended means to check the displacement also in the y direction, whether support is resting on the steel or it is lifting. So if it is showing in 0 like this, you see in dy direction, then your support is exactly resting on the steel. If it is showing any positive direction or in positive value, then your support is lifting by that much mm. Okay, I will show you, you will see. So in this cases also all supports are resting. And if you see at node number 1130 plus y, in hydro it is taking load and in operating it is showing 0. If it is showing 0 means that support is going up. So if you check the displacement at that particular dy at the particular case, you see it is 0.147 mm, it is lifting. It is just 0.147 mm only. So generally up to 2 mm we can allow in the displacement. Okay, 1 to 2 mm we can allow. So if the displacement is 1 or 2 mm, just we can allow. So you see in all other cases also it is lifting by 0.157 mm. You can leave like this. And in the anchor, so why we are considering anchor? It will not be a real anchor. In order to get the moments. So wherever you are providing anchor, there only you will get the moments. That means the 6 degrees of freedom will be arrested. Means displacement dx, dy, dz and what is that? Rotations or x or y or z. If displacements and rotations are provided, then only you will get fx, fy, fz, mx, my, mz. Okay. And if you check this support, this is taking load, that is good. And if you see all are showing -0, that means it is resisting. So this support also it is taking load. But you see in this case, in some cases it is showing 0. That means it's in positive, means 0.010 in the positive direction, in the upward direction. So that support is lifting by 0.01 mm only. You can leave like that. Okay. And also you need to check the variation between the load cases. And for example, sustained and operating load shall be 20 to 30% margin difference can be there, that is allowed. But if there is a huge difference like 60% or 70% difference, then you have to check the supports. See in this case, that means your support is not at proper location, it's not balanced on. No? So your sustained case is 11,000 Newton and in your design case is 19,000. So if the design case there is a variation, more variation between design case and sustained case, which you can check the operating case, operating temperature. So operating temperature is almost it is 13,000 and it's 11,000. So it is okay. 2,000 Newton only difference is that is okay. So 20% to 30% variation you can allow. And you see in this case we have given Y, guide and limit stop. All three directions we have provided support. So without gap. That means you see in all three directions it is showing 0. So in Y direction it is taking load, and in X and Z direction also it is 0 because we have provided 0 mm gap. You see 113030, this anchor, yeah, you need to check properly. This anchor you need to check because anchor should not values of 0. That means this anchor is not properly entered by us. So you have to check 113030, go to 11,030, 11030. So 113030, you have entered the C node as 10.71. That means your mistake is identified, you can easily identify the mistake. So your C node should be this node, from node, no? You see, this is some other node. So you need to change this C node 10171, this to this from node. It should be 10171 here. Now if you run the system, you can easily identify. I told you know this. So here only we have not given any gap. That's why it was showing 0 mm in the direction. If you provide 3 mm, just I am showing 6040. Just I am giving 3 mm. Run the system, and this node number also you remember. What is it? 113030. So you select hydro all operating cases and sustain case. Go to restraint summary extended. Go to 113030. You see, now in 113030 you are getting the loads. So if it is showing 0 means that your input is having some error. So you have done a mistake. Like this you can easily find out the mistake in restraint summary extended. If you go to here, I told you now we are given gap for the guide and limit stop. We're giving gap. So here we have given 3 mm gap. Okay, but it is yeah, you see maximum is 3 mm. And here also maximum is 3 mm. Okay, so whatever gap you are giving, that will be highlighted here. So these loads has to be checked with respect to your pipe support standard. In pipe support standard, they used to give some vertical load as well as horizontal load. So you need to cross check the loads. You need to compare the loads with respect to the pipe support standard. If the output loads, whatever we are getting in CAESAR, if it is lesser than the values provided in the supports, then it is good and you can select that support. I will show you where the lift offs are there. We'll go to the other model, the steam line. We'll go to the steam line. So here we will check the restraint summary. Okay, because since the temperature is more, well, lift off is also more. So hydro sustain, hydro operating and sustain. Select restraint summary extended. Okay, you see at 150, 80 it is okay, it is 0 only, and all are in negative direction. But at node number 150, you see in hydro it is taking load, and in sustain it is taking load, but in operating cases it is lifting. See 47.27 mm it is lifting, means the support is not taking load. On we'll go to that node number 150. 150. Yeah, you see. Yeah, this is a typical example we are working for other plants. So in this case, for steam lines, what we will do if the movement is more or if the displacement is very high, like this, that means what happened means this support is moving upwards during operation. Why means at the bottom you have, I think you have one support. So this support, what's happening means this support is pushing this pipe upwards. So this pipe is moving like this, and it may like this. That's why the 47 mm lift up is there for this support. So in this case, for steam lines, what we will do, we need to use spring anchor here if the displacement is very high, because see 47 mm generally will not allow. So in those cases only you need to select the proper supports. I mean, yeah, you have to go for spring anchor. And at node number 170, you see the displacement came down. Means I told you, the movement will be like that only. So this support is pushing this pipe towards upwards, and what happens like this, gradually it will come down. So here the movement is reduced to 5 mm. I mean the lift up is reduced to 5 mm only, 5.9 mm. Okay. Sorry, here you can use rigid support. This support is okay. Up to 5 mm it is okay. So you can leave like this. But this 47 mm you have to go for spring anchor. Sorry. Or bottom spring anchor you can go. Okay. Then we'll check other supports. See other supports and all taking load. And at node number 210, you see at node number 210 you have rest support plus Y, guide support, and limit stop is there. Means limit stop is in Z direction. Okay, so your guide support is okay, and vertical load is 2561, and you see your limit stop support is nearly 4 times more than the vertical load. So always you try to avoid this one like this. Your vertical load should be more. I mean the horizontal load should not be more than vertical load. If it is more than vertical load, then you have to cross check. Anyway, you need to cross check the horizontal loads with respect to the guide loads and limits of load provided in your support standard. Okay, I will show you the support standard later. We will see how to cross check the loads and all while doing support engineering. Okay, so you have to remember this. So the maximum load will be there, that will be given your support standard. If the maximum horizontal load is exceeding, then we will go for the special support. So these supports and all, it's okay. And again you see this support is 3 mm, it is lifting, okay, we can leave. And this support is, see, at node number 710, go to 710, sorry, 710. Node number 710, you didn't find anything in X and Z direction. That means you have removed the friction at this node. Because plus Y, if you give only plus Y, your vertical load only will be there. Plus Y plus coefficient of friction, you will get the horizontal loads. Or if you have guide supports, then you will have horizontal loads. You see here, there is no coefficient of friction. That's why it is showing the values in y direction only. Okay. So in all these supports, they removed the coefficient of friction 740, 770 because of that non-convergence error, I think so. 740, 770 at all node numbers. So like this, you have to check all the supports with respect to the displacement as well as with respect to the loads, vertical as well as horizontal. And lift off is very important, I told you, no? So mainly you have to check the limits of flow for the pipe rack lines. That is very important. Because we need to transfer the loads to the structural team to design their member. If you give more limits of load, then it is difficult for them to design. So you see all other supports are taking load, and you see at node number 3410, vertical load is 7000 only, but your horizontal load it is 11,000 Newton. 3410, go to 3410. X direction, X is limit stop, you see. So that means your limit stop load is more. So you have to concentrate on the limit stop load for the pipe rack lines as well as lines running on the sleepers. So like this, all loads shall be checked. Okay. So then we have 1 minute. I will. Yeah. So we have checked the stresses, displacement, and restraint summary. If everything is okay, then we'll go for nozzle load check. That we'll see in another video. Thank you very much.